6.5, trigonometric form of a complex number. Objectives. There's 4. You can pause to read. I am moving on to the next slide. Vocabulary key concepts. Same as the previous slide. You can pause to read. I'm moving on to the next slide. This is a formula, trigonometric form of a complex number. The trigonometric form of a complex number, this is what you saw in algebra 2. This is a complex number, and then we can rewrite it in trigonometric form, and this is how it looks. We can rewrite this complex number in trigonometric form, and this is what you need to do. A is equal to r cosine theta, B is equal to r sine theta. R is basically the radius of, or the radius, which is the square root of a squared plus b squared, whatever this is. And you did this in algebra 2. So we call the absolute value of the complex number. And then the theta is generated by this trig ratio, b over a. This is your b, this is your a. You're going to be using reference angles to find the exact theta. Next slide. It says represent the complex number graphically and find the trigonometric form of the number. Trigonometric form is right here. So we need to find the radius theta. So let's graph this point. Notice it is another quadrant. So we need to generate the r, find the theta. You should see that this is, let me use red. This is your radius. And the way that you find the radius, you can think about it as a right triangle. Just use my right triangle here. And find this distance, which is 3. This distance, which is 3 radical 3. I ignore the sign. They're both negative. So if I use the Pythagorean theorem or the formula you saw earlier, or the formula used in algebra 2, this is how you get 6. So distance from here to here is 6. Then at this point, what I need to do is I need to find this theta, but this is actually theta prime. This is your theta. So first I find theta prime. To find theta, I add 180 to theta prime. So how am I going to do this? I'm going to use a tangent trig ratio. I get the following: opposite over adjacent. Do the inverse, I get 60 degrees. So this is my theta prime. How do I find my theta? I add 180 to 60, and that's how I end up with 240. And I use the radian measure of 240, which is 4 pi over 3. And this is my answer. This complex number in trigonometric form is equal to this. Next slide. Same directions as number 1. I want to make it look like this. I graph the point Z. Again, I can find the radius using the Pythagorean theorem. Once I draw this right triangle, this is my theta prime. To find my theta, I have to find theta prime and subtract that from 360. So then to find the hypotenuse, or to find the r, this is what I do. I plug the information into the formula. Notice that this, once you distribute, you end up with this. Once you distribute the 5/2 to the second term in the complex number, you end up with this. And then work with these numbers and you end up with 5. At this point, I'm going to find theta. The distance from here to here, you know, that is 5 over 2 radical 3. From here is negative, or actually forget about the sign, this is 2.5. So then I work with tangent to find my theta prime. This is what I end up with, 30 degrees or pi over 6. To find my theta, I take away from 360, I take away 30, and that's how I end up with 330, or 11 pi over 6. So the complex number expressed in trigonometric form is the following. Next slide. Next formula is the product and quotient of two complex numbers. So these are the two complex numbers that we're working with. Excuse me. This is the first complex number. Notice you have radius, cosine, sine. This is the first complex number. So that's why you see sub 1, sub 1, sub 1 here. Second complex number, that's why you see sub 2, sub 2, sub 2. You can use this notation. So to find the product of these two complex numbers, z sub 1 times z sub 2 is the following. You take the radius, you take the r, and you multiply them together. And then cosine and sine, and all you do with the angles is just add them. So theta sub 1 plus theta sub 2, that's what you have here. Same thing for sine, theta sub 1 plus theta sub 2. The quotient is a little bit different. Instead of multiplying the radius, now you're going to divide them. And then instead of adding the thetas, now you're going to subtract them. Just a little technicality because we want to get rid of the value when it's undefined. Next slide. Supply these formulas. Perform the operation and leave the result in standard form. This is standard form, what you see here, cosine, sine, whatever. So if I use the formula, this is what I need to do. I need to multiply the radius, cosine, sum of these two angles, which is what you see here, I sine, and then the sum of the two angles. At this point, I know that this gives me 9, and then pi over 6 plus pi over 4 is 5 pi over 12, and this is the answer to number 3. You're done. This is what we call standard form. You leave it in standard form, or trigonometric form. Number 4, now you're taking the quotient of two numbers. So then you apply the second formula you saw. So you're going to divide the radius, and then you're going to subtract the angles. And this is what you get. 5 over 3 times, and divisions get the reciprocal, or just multiply top and bottom by 15 over 1. And that's how you end up with this. And then at this point, all you need to do is just perform some simple arithmetic. And this is your answer. 25 cosine 3 pi over 4 plus I sine 3 pi over 4. Next slide. This is the Mauver's theorem. Very nice formula. You get a pen. So you have a complex number, and we can express any complex number in trigonometric form. So whenever you have a complex number raised to a power, this is what you can do. Express the complex number in trigonometric form and then apply this formula. All you need to do is take the power that you're raising the complex number to, take the radius, raise it to that power, and then cosine of n times the theta, I sine n times the theta. Very nice formula. This French individual, Demoivre, came up with this. So let's apply this. It says use Demoivre's theorem to find the indicated power of the complex number. Write the result in standard form. So if I apply the formula you saw on the previous slide, which is there, all I need to do is the following. You give this exponent to this base, and you have 3 to the 4th. I rewrote this in degrees. You don't have to. You can work with radians. And then I multiply 4 times the angle, 4 times the angle, cosine, I sine. Once I simplify that, I get 81 cosine 600 I 600. I'm going to use a reference angle that is between 0 and 2 pi, or 0 and 360. Turns out to be 240, and you know how to find reference angles. And then at this point, I just basically use the trig ratios from the unit circle, distribute the 81, and this is your answer. Number 6. Same for directions. Now the only difference is here you're not given trigonometric form, so you're given a complex number. So what you can do is you can rewrite any complex number in trigonometric form. So by doing a little bit of work, you should be able to see that r is equal to 2 and the theta is 5 pi over 3. This is how we did number 1 and 2 on this video. So then, once I substitute the values into that formula, this is what I get. And notice that this 4, we just bring it down. It's like a constant. It's like a scalar. So then all of this that you see here became what you see here. Oops. Excuse me. Let me do this again. All of this is this. The 4 is this 4. And again, this is the formula that we're going to be using. So at this point, give this exponent to this base, multiply the 3 times this angle, 3 times the second angle. I get the following. I bring over the 4 in front here, the scalar, the constant. This gives me just 5 pi for both angles, and then this is just 8. I simplify this. I multiply 4 times 8, which is 32. Cosine of 5 pi is -1. Sine of 5 pi is 0. So the answer is -32. If you were to actually do this problem the way that you were shown in Algebra 2, all you need to do is you need to multiply this base 3 times. And you should be able to get the answer, but it's going to be a time-consuming process, and hopefully you don't make a mistake. Not only that, what happens if I give you a power that is more than 3? You'll be here for a while. So this French dude, this French individual, you should be thankful because his formula simplifies the amount of work that you have to do to expand something like this. Next slide. It says same directions. Notice that now you have to the 5th power. So it will take you a little bit longer if you do it. If you use this, excuse me, I'm trying to get red. There it is. If you were to use the skills that you develop in that you learn in Algebra 2, you'll be here for a while. If you use his way, the Mauver's theorem makes your life a lot easier. So you should know how to get the radius, you should know how to get the angle, and then at this point I substitute. This is what I get. I apply the Mauver's theorem, give this exponent to this base, multiply the 5 times each of these angles, and I get the following. Simplify. This becomes 32. Multiply 5 times this 5 pi over 6, and I end up with the following for both angles. At this point, I'm going to use another reference angle. 25 pi over 6 is the same thing as pi over 6. So then I simplify this using trig ratios, the unit circle, and I get the following. Multiply the 32, distribute the 32, and this is your answer. Very, it's not a complicated process, a little bit time consuming, but if you were to use the skills that you use, what you did in Algebra 2, you'll be here for a while. Going on to number 8. Again, same directions. This one's a little bit different. Notice that now you're raising everything to the 5th power. not only this inside the parentheses, but also what's the constant outside. So then this is what you can do. Give this exponent to this base, and then now you're going to work with this. In a little bit, we're going to work with whatever this is. So I use my what I learned in this video. I can rewrite any complex number in trigonometric form. First, I find the radius in that theta. This is what I get. I substitute, and this is, excuse me, this complex number that you see here, expressed in trigonometric form, is right here. And 3 to the 5th power is 243, so I just bring it over. So this is going to be a constant that I'll take care of at the end. So now I apply the De Moivre's theorem, give this exponent to this base, multiply this 5 times the angles. I get the following, and then I'm going to simplify this a little bit. All it is, once you multiply, becomes 7,776. When you multiply this radian times this 5, you get the following. I'm going to again use reference angle. 20 pi over 3 is the same thing as 2 pi over 3. And then at this point, I simplify this using trig ratios. Get the following. I'm going to distribute this constant. And this is my answer. This concludes the video.